So let's start analyzing some circuits using Ohm's law. So this in general is called circuit analysis. Or solving circuits. So we solve for everything we can, solving circuits. We'll do a couple things. The first thing I'm going to do is we're going to work in pair and series. We'll define all this stuff as needed. So I'm going to hook up a battery to a single resistor, just to review Ohm's law real quick. So I have let's do a 9-volt battery connected to a 5 ohm resistor. So in this case, I have the resistance of the circuit, that's 5 ohms, and I have the potential. So the current would be delta V over R. So the current would be 9 fifths. And that would be, let me get it in decimal. Divided by 5, 1.8. So we get a current of 1.8 amps. Alright, so let's hook up the same thing, but now I'm going to hook it up to 9 volts. And it's going to come around, and it's going to go across a 5 and a 5. This will allow us to see like what happens to the current and potential and all of that. Okay. Oops, that's negative. Let me just do that. I don't want you getting confused. Okay. So we'll say this is 5 ohms, and this is 5 ohms. So equal resistors. And let me switch color here. Okay. So what I want to know is I want to know everything. I want to know the current coming this way. I want to know the potential difference across each resistor. So we'll call it potential difference 1 or potential difference 2. So as it goes across, we know that it drops, but it doesn't go to 0 after one of them like this one. This one, the potential difference, was the 9 volts as it went across. But this one, it's probably going to be 4.5 because these are equal. But we don't know that, and we don't know the current. So we need to figure some stuff out. So what we have to do is we're going to build what's called equivalent resistance. Equivalent resistance. And the idea, this is how you solve circuits. So what we do is we just start putting all of the resistors together until we get something that looks like that. Because this is easy to solve. So we'll get everything put together until it looks like this, we'll solve for it, and then we start breaking it back out and working backwards. So the process gets a little lengthy, but the math and stuff inside of it is pretty easy. It's just putting stuff together. So equivalent resistance. So this goes step by step, and we just start adding stuff, or sometimes we got to invert it. It depends on the configuration. So for this one, since these are lined up, or one right after another, this is called in series. In series. So these resistors are in series. They're one right after another. And then we'll do parallel. Let me show you on the equation sheet. So what we get is, we get these last two right here. So the equivalent resistance in series, that's the little s, is equal to the sum of the resistances. So all we have to do is add them up. I'll write it here. So the resistance in series is equal to the sum of the resistors, or the resistances. So in this case, my equivalent resistance, I'm going to put EQ, is equal to 5 ohms plus 5 ohms. So we get a 10 ohm resistor. So what I can do is we have to redraw it, and this is key. You're not going to want to do this, but trust me. We're going to redraw it, and this creates an equivalent resistor of 10 ohms. So now I know I have 9 volts, and I have a 10 ohm resistor. So I know the potential difference across this resistor, the equivalent resistor, is 9 volts. And with that, I can figure out the current. So my current is going to be the potential difference divided by the resistance. So I get 9 divided by 10, or 9/10, 0.9 amps. So you can see what happened. I went from a current of 1.8, I doubled the resistance, and I got half the current. And that makes sense. You know, if I double the resistance down here, I get 1/2 the current on the other side. So we get less current moving around it. Same potential difference across the equivalent resistor, but less current. All right, so now that I have this, now I can go back here and I can figure out the potential difference across each of these. Now I know the current is 0.9, and that's everywhere. You have to remember that. That's the current everywhere. I don't have any junctions. If I had a junction, then that doesn't apply because the current will split up. But basically, my current across this resistance, this resistor, is 0.9. So I can find that first potential. So let's go over here. So that change in that potential is just I times R. That's just Ohm's law rearranged. So I just multiply the 0.9 times 5, and I should get 4.5. Yeah. So we get up 4.5. So that's equal to 4.5 volts. And over on the other one, I'm going to get the same thing. That's whatever's left, 4.5 volts. And I'm done. I solved the circuit. I know the current, the potential, and the resistance for every resistor. Let's try another one, but I'm going to change the resistance so you can see. Oh no, I'm going to draw a little bigger. So there's my positive and my negative. We'll go up and over. Like heartbeats instead of resistors. Oh, I got a new microphone and it sucks. I'll get it fixed though. Let's say we have a resistance of 2 ohms and then a resistance of, let's do 3 ohms. Alright, and then we'll hook it up to a 10-volt battery. So I know my current is coming around this way because it leaves the positive and goes around to the negative. I know it's the same everywhere. So what I'm going to want is I'm going to want the potential difference across resistor 1. I need the potential difference across potential resistor 2. Put the 2 and 1. And I need the current. And so it seems like you don't have enough information, but what we do is we squeeze stuff together. So we can sketch this really quickly. So I have 10 ohms and it's only 2 resistors and they're in series. So I'm going to put them together into an equivalent so that I can figure some stuff out. So they're in series, so I just add them up. That's 2 plus 3 is 5 ohm. And I got 10 volt. So I know my current using Ohm's law. Current is potential difference divided by resistance. So I get 10 divided by 5, which is 2. So I got 2 amps coming around. Alright, now we go back one step. Boom. So my current here is 2 amps. 2.0 amps. So I got 2 amps across this, and I got 2 amps across this. So I want potential difference. Well, potential difference is Ohm's law rearranged, is IR. So potential difference 1 would be the current, 2 times the resistance, 2. So I get 4 volts. And potential difference 2 is going to be 2 times 3. So I get 2 times 3 is 6 volts. So here it drops 6 volts, and here it drops 4 volts, leaving me with 0 volts coming back in. You always want to check it, so you make sure that these add up to be that. Yeah? Alright, so this is in series, and then we're going to do parallel. In series, you get the same current, so this current equals this current, but different potential differences. In, put I1. So in the next one, what we're going to see is we'll get different current, but we'll get the same potential difference. And that's a key distinction. So let me clear this. So this is our other one that we talk about, and this is in parallel. So if I have a battery attached to two resistors, like so. So now that they're not one right after another. Okay. So let's say this was, we'll say 3 ohms, and this one is 4 ohms. Alright, so let's throw 9 volts on there. Alright, so we have some current that's going to come around. This is I, we'll call it I1. I1, and then it's going to come over here, and then it has a choice. So the charges can go this way, or they can go this way. And what will happen is some will go this way, and some will go that way. So we'll get I2 coming this way, and then we get I3, which would come all the way around here. And then what's going to happen is they're going to recombine, and I'll get I1 again coming this way. So I can see I'll have a different current here and here because I have different resistance. Now, since this one has more resistance, I'm going to get higher current on this one because this one has less resistance, so I can get more charge passing through it. But how do we analyze this? So looking at the equation sheet, that's the last equation, this one right here, and it's these inverses. So it gets a little tricky, but it's still pretty straightforward. So what we have is the resistance, the equivalent resistance in parallel is, it's 1 over the resistance in parallel is equal to the sum of 1 over the resistances. Those are all of them. So here's how we set it up. We do 1 over Rp is equal to, it's going to be 1 over 3, that's the first resistance, plus 1 over 4. So we get 1 over Rp is equal to, let me think, 12 and 12. So that's 4 times, so we get 4 plus 3, 7/12. The thing is that this is 1 over, so we need to invert this. So my equivalent resistance for the parallel is going to be 12 over 7, which is 12 divided by 7, 1.71. So we get an equivalent resistance of 1.71. And this is important. So notice in parallel, I had a 3 ohm and a 4 ohm, but my equivalent resistance is only 1.7. So when you hook up in parallel, your resistance goes down. So let me write that in red. So in parallel, resistance goes down. In series, resistance goes up because we add them up. This one is an inverse. One thing on the math, what I normally do is I'll just put this whole thing in a -1. So I would do like my resistance parallel is equal to 1 over 3 plus 1 over 4 to the inverse, because I could just enter all of that in my calculator and that would come out. A little quicker to do it this way. Okay, so we can put this together. So now I have a 9 volt. Let me change this. We have a 9 volt, that's positive, this is negative, connected to an equivalent resistor. An equivalent resistor of 1.71 ohm, 9 volts. Alright, so what I can do is I can calculate the current now. So current, again, is delta V over R. So my current is going to be 9 divided by 1.71, 5.26. So we get a current of 5.26 amps. That's here. That's coming out of the battery. So I1, that's this one, is equal to 5.26 amps. Yeah? Alright. So then we go back, and so we know I1. We know I1 is 5.26. I'm going to change to red because this is pretty important. In parallel, all the potential difference across the branches is the same. So this potential difference here is equal to this potential difference here. And they're all equal to the original one, 9 volts. So over here I get 9 volts. And here, 9 volts. I'll summarize this. But in parallel, we're going to get the same potential difference. We'll get different currents. In series, we had the same current and different potential difference. So now we can figure out the current in each of these. And remember, current is just this divided by that. So my current here on I2, this is getting messy, I2 is equal to 9 divided by 3, which is 3 amps. And if I come over here, this would be 9 divided by 4, so my current 3 would be 9 divided by 4, 2.25. 2.25. So when they come back together, I would add 3 plus 2.25 to get 5.26. There's rounding in there. Alright, so then I have the next video looks at these complex ones. We'll practice this if you come after school. Let me just summarize this stuff real quick so clear. So in series, it's stuff that looks like this. You get resistors like that, and you'll have the same current and possibly different potential difference. The reason it's possibly is it depends on the resistance. If you have the same resistance on each of these, you'll get the same potential difference. But anyway, they can be different, but you always have the same current. In parallel, that's looks like you see how they're parallel. You get the same potential difference and possibly different current. And then to find the equivalent resistance here, we just add them. Oops. Whoa, 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 whoa. Okay. Oh. There. Here we just add them. So it's the sum of all the resistance. Over here it's the inverse. I'm writing it like it is on your equation sheet, but for this one, I would suggest you do it like this. Alright, and we'll practice in class.